Good. Good morning for those who are joining us in their unscheduled class online. We are about to start the class. I'm just going to start by sharing lecture 4, an introduction of soils, which is the topic we're going to start with the class today. Okay, for those of you in the room, welcome to Agronomy 1, and I will just share the screen. All being well, it did work this morning when I set things up, but yay. Okay, that's good. All right, soil. Good stuff, hey? This is what we're going to be talking about today. I'm just going to shut the door. And this is very fundamental to all agronomy. Oh, thank you. Thank you. Yeah, shut the door. So I thought I'd bring some to class because it's always good to have a look and a feel. And what I'd like you to do is pass this around and maybe just rub it in your fingertips while we're thinking about this stuff, this amazing stuff which we call soil. And let me just start this slideshow. Now, there are people that have spent a whole lifetime studying soil and they still don't know enough about it. So we are not going to pretend after this one lecture on introduction to soils that we have got everything we need to know about soils and agronomy. But you are going to start with the fundamentals on soil. This is just meant to be an introduction to the topic of soils and how you might manage soils. And in the subject ecological systems or study, ecological systems, sorry, which you do in your second year, and that's really where Doug Rao, who's our soil expert, will take you into some great depth. So this is just an introduction. So all we're going to do is introduce how soils enable plants to grow. So in this topic, we're going to introduce soils. We're going to understand, hopefully, why soil is so important to agronomy. And then we're going to talk about the key components or characteristics of soil, which are texture, structure, soil pH, cation exchange capacity, and fertility. My soil's returned. Thank you. I'm going to demonstrate this in a bit. Okay, so what is soil? Well, very simply, it's a substrate. And depending on where you live, it can be many different things. So I think that's the very first important thing to understand about Australian soils. They're very, very varied. So soils can be composed, and mostly are composed, of mineral, organic, organisms, micro and macroorganisms. They have space in them. They're not all filled up. If you were to blow them up and to take a microscope, very high resolution, that you would see that there was space in these soils as well. And there's liquids and gases in soil. So it's an extremely complex matrix of components. To understand soils well, you have to understand a little bit about geology and time and how the Earth evolved. And time plays a very, very important role in soils. So millions of years ago, Australia's was, when it was under sea, just after it moved away from the sea, its soils then would be quite different to its soils now because there has been a considerable amount of time. In the evolution of soils, a day isn't significant, nor is a week, nor is a year, nor are simple lifetimes, but many, many lifetimes, hundreds and thousands of years, tend to be the scale, long periods that affect rocks. So you have chemical changes in that time, you have physical changes in that time, mostly brought about by weathering. And you have huge variations of biological factors changing over that time. Particularly if you had sedimentary and igneous and metamorphic rocks. There's some really interesting pronunciations in some of these words, so I do my best with them, but you'll have to excuse me if I get some of them wrong. When we say weathered, we are talking about biochemical weathering as well as the weathering of the Earth's crust and how that impacts on your surface. So that's basically the overview of soil. I'm going to quickly stop to a video that shows a bit about how soils are formed, and there's some diagrams in this which are quite good. So let me just share. Excellent. Now, don't worry too much if you can't hear what's being said. You can go back and listen to this in your own time, but I am hoping that you will be able to hear it today.
I have another quick video on Earth systems. We're going to talk specifically in this case about soil formation. How do we get from the rock cycle?
Sorry?
Obviously come from the crust and the tectonic plates. How do we get from all that to the soil?
That is the video.
That obviously is going to have a pretty much
sorry, I
direct
gotcha.
impact on human and all really biological life.
I didn't have to do this last week. It just worked. All right, here we go. Yay. All right.
Essentially what soil is a mix of geologic and organic components. So you've got parts of the biosphere here that as they die and decay, they get deposited, and of course they're manure and stuff like that. Then you've got parts of the geosphere, which are the rocks being broken down. You need both of these things together to actually make soil. So like if you just have sand, things don't grow well in sand. That's just the rock. And so for it to actually become soil and to grow, you've got to mix in organic matter with that. That's why if you've got really sandy soil, then it's usually necessary to either mix in some fertilizer or some manure or some compost or something that gives it some organic components. So that's really what compost is. Compost is organic components that are going to decay down. And then if you mix those in with the rock components, some dirt, some clay, some stuff like that, then it can become actual soil. So two parts here. You got the breakdown of the rocks, you got deposition of organic matter. Those two things together are going to create soil. So we talked about the breakdown of the rocks in the rock cycle video that we did before.
So this is the first figure I want you to take on board. You have rocks and you have organic matter, and that equals soil. I will tell you the most important things that you need to take away with you, because I know that the volume isn't very loud. But you will see some good illustrations in this.
For this, the deposition of organic matter, again, is as things die and are broken down by bacteria, stirred up by earthworms, stuff like that, manure being deposited, all of those things are going to go into making proper soil as well. And there are basically 5 factors that are going to affect what the soil is like. We all know that different kinds of soil are going to be used, are going to appear in different areas, are going to be used to grow different things. So the first thing is the parent material. So what kind of rock is actually being broken down? And so it's a little hard to see in the video here, but this top example, this is some granite. And if that's broken down, you tend to not really get super rich soils because the granite has a lot of silica components in it, which you think about sand. And so it's not going to be very nutrient.
So here he's talking about granite, and it has some sand, and he's stating that it's not very nutrient filled. And there's an image on there which, when you watch your YouTube from your computers, you'll be able to see the resolution.
Rich just from the rock component. Now, of course, if you add organic component to it, that's what makes it soil, and that's what helps out. But on the other hand, if something like, say, limestone breaks down, limestone is essentially calcium, and so the calcium that's in that is going to actually be one of the active nutrient components of the soil. And so the parent material, what kind of rock breaks down to actually form the rock component, is pretty important to what the soil is. Climate obviously has a pretty big effect on this. The temperature and precipitation particularly are going to affect how quickly the soil forms. Soil is not going to form very well typically in really cold climates.
He's now talking about climate and how the climate influences how the soils are formed, and cold is particularly slows down that development of the soils.
But in warmer climates, and particularly in climates where you get a lot of precipitation, and therefore a lot of weathering, a lot of erosion, a lot of deposition from that precipitation, then the soil is going to form much more quickly. And that's why in tropical areas you tend to see much richer types of soils. And
that's a really, really important part about soils, is the weathering and the impact of water. When we're growing plants, we're moving and utilising the soil a lot more than natural communities as a whole. Of course, pastures can form a bit of an exception here, but mostly you are turning over the soil, you're planting in it, it either rains and or you're irrigating, you're growing your crop. Next year, then you're harvesting your crop, you're putting machinery over that soil the whole time, then the following year you're doing exactly the same thing. So every single time you go in there, you're making physical changes. And when those physical changes are coupled with water, the impact becomes far greater. And water is really, it's a double-edged sword. It's good, but it's bad for soil texture because it does break it down. Again, over time. Not over 1 year or 2 years or 3 years of farming, but 40, 60, 80, 100, several hundred years, you really do start to see the impact, particularly if you haven't managed your soils well.
Temperate regions, obviously, as compared to, say, Arctic regions, you're going to get much better soil out of that. The third thing that is going to affect the rate or affect the soil formation is topography. In other words, how steep is the land? It tends to be, just generally speaking, that the steeper the slope, that the more quickly it's going to erode, because the higher up it is, the steeper it is, the faster the water is going to flow down it.
So this is talking about how steep a mountain or hill is. Now we see that at Yang Ying. When you remember when you were out there for the weed workshop, and we'd come out of the classroom and we'd walked along the driveway there and we were collecting weeds. Well, if you'd have looked in front of you, you'd have seen quite a big hill up in the distance. And we do see soil degradation at the top of that hill. We see it when it rains a lot, when it's very cold, but also if there's a lot of wind, and if we don't manage the vegetation on the top there, the erosion is quicker. So in the past, they used to do practicals with digging up there, and that soil erosion was really, really quick. Even though they would dig, move the soil, then replace it, because the soil had been physically moved, and then it would rain, and then there would be more wind, and then there wouldn't be much plant life on there. You can see quite a lot of movement very quickly. So we do have to manage that as part of the farm. Even though it's not a productive area of land, we don't want that soil movement. We want the soil that we've got on our paddock, not that soil up there, because we're not managing it for plant growth.
Or it's probably going to be subjected to wind. All of those things are going to weather and break down the rock and then lead to soil formation. What kind of organisms are in the area? And so again, this works against Arctic regions because there's not quite the vast variety of organisms. And so plants and animals are going to take nutrients out of the soil. Bacteria and stuff are going to break stuff down. Earthworms are going to help to mix up the soil. And so all of those things together are the organism, the biological part that's going to help to start to make up the soil. The fifth component is time. Okay, so the longer the time goes on, in general, the more what we call mature the soil. Now, the reason that we call it more mature soil is A, the particles of the rock are usually broken down much finer. And then secondly, there's going to tend to be a lot more organic material there. So, like for instance, if we were talking about like a volcanic island that just formed, some of the rock might be a little bit broken down. So if we're talking about like a volcanic island that had just formed, some of the rock might break down, but until animals start to come there, and you might get birds and stuff like that, obviously going by, but you're not going to have a lot of organic matter, so it's going to be a very immature soil. As time goes on, and that volcanic isle ages a little bit, the rocks break down a little bit more plant life starts to come in, seeds get dropped by birds, stuff starts to grow, break down the soil more, it dies off and forms more organic material, and then it's time, so I can get a much more mature soil out of that. Okay, so let's talk a little bit about the layer.
So that previous slide showed the change over time from very immature soil to very mature soil. Where do you think in Australia we are soil-wise? Are we a young country or are we quite an old country? We're a very old country, yes, very old. And managing our soils presents very interesting challenges because of that concept. You can listen to this in your own time. There is a link on the URL, but the rest of it I'm going to talk about in the lecture, and I just wanted you to see those first couple of figures. Okay, just bear with me a moment. Very difficult. Cool. Okay, so the factors that affect soil are the parent material rock, as we've seen in that previous video. These affect soil chemistry. We have temperature and water, very important. Topography, diversity of organisms, and the fifth one is time. So that's a really good summation list for you to remember about how soils are impacted. So what is a soil profile? So let's start off with a very simple question. Do you think that the soil is uniform? No, because you've all seen that, haven't you? Who's dug a hole here? Who's dug many holes? It's not uniform at all. And what you can do is separate the soil profile into components, because there are characteristics that are quite specific depending on how deep you get. So when we're looking at the surface of the soil, all the way down to where the soil ends, that's called the soil profile. We, as agronomists, will use only some of the soil profile. Why is that?
You don't have to use like a certain amount of depth.
You do, yeah. That's right. Different plants require different depths. Different plant roots will grow in different ways. And how far a plant's root grows down will depend on a suite of factors in that soil, as well as the plant's own genetic factors. So things like whether it's a monocot or a dicot will change how the root structure grows, which will change how that plant will explore the soil that it's grown in. The physical aspects of the soil will impact how the plant grows, and you're going to learn a lot about that as this lecture goes on. Yeah, tell them I'm busy. And also the chemistry has an impact as well as the biology and time. So all of those things in that list, hi, how are you going? Has impacts on how the plant grows. So let's look at the soil profile and how it's divided into, here's some technical terminology now, we call them horizons. So here's an overview of the horizons or breakdown of the soil. So right at the very top of the soil, let's see if I can find them out. So you see you've got the grass or whatever's growing on the top, and then you've got 1 millimeter of soil surface, and that is what we call or refer to as the infiltration layer. It's usually 1 or 2 millimeters thick. Do you think that's important? Yeah. And do you think it changes depending on where you are? Yeah, it does. And the Department of Primary Industries was doing some really interesting research out in Horsham Way a few years ago, where they were looking at dairy pastures and seeing how different types of infiltration layers, so different characteristics, change what nutrients and how the rain and water gets through to the plants. And that's really important, because if your infiltration layer is not ideal for your growing of your plant, then you can imagine it start to rain and the water just lands on that infiltration layer. And rather than going through the infiltration layer, which is what you really ideally want, you can have a greater degree of runoff, because that infiltration layer, if the soil's not managed correctly, can become what we call hydrophobic. Do you know what hydrophobic means? Yeah, water hating is a good layman's interpretation of that. It's describing the physical entity of the compound, hydrophobic, and the opposite to hydrophobic is hydrophilic. So infiltration layers on the top of soils, do we want them to be hydrophobic or hydrophilic? We want them to be hydrophobic, do we? Maybe if we're making a dam from our neighbour's property, we might want to. No, we want them to be hydrophilic. We want them to absorb as much of that rain as possible. If it hasn't rained for a while, soils, and you've probably noticed this in your garden or if you have pot plants, soils will not absorb water immediately, because if they haven't had water in them and they've dried up, they will become hydrophobic. And this is a little bit of topsoil, which includes infiltration layer, and it also includes A horizon. There is no B horizon in this soil, and because of where it was, I suspect it will have hydrophobic characteristics, which I'm hoping to demonstrate in a little bit. So that's my sample of soil. So next we have the A horizon. This is also known as the topsoil, and this is where seeds tend to germinate. Okay, cool. This can vary in thickness. It can be a couple of millimeters deep, or it can be 10, 15 millimeters deep, depending on where you are and how your soil structure is composed of, where you made your soil. Roots will infiltrate this area. They don't infiltrate the very top, the first couple of millimeters, because that's too subjective to drying out. So they don't tend to go right along. Although you do see some plants, there are some trees that will deliberately go outside and then back in, but that's part of a structural component rather than anything else. This is followed by the horizon B, and horizon B is probably the most important horizon as an agronomist, because this is usually where most of your productive root zone occurs. So horizon B is usually split into B1 and B2, just to add a little bit of confusion. But that's where you'll find most of your roots. That's where you'll find most of your water uptake and your nutrient uptake. If you have the right suite of nutrients in the soil, and you have the right amount of water, and your soil is in a hydrophilic or water-loving chemical condition, then you should get good nutrient uptake. If your soil is hydrophobic, if you're lacking in water, you might not get ideal nutrient uptake. So the B1 and B2 horizons are very important for us as agronomists. Then we go down to C horizon, And this varies in how deep it can be. It can be as less as 20 centimeters in some instances, or it can be as deep as 1.5 meters down. It does really vary wherever, depending on where you are and the construction of how your soil has been made. This layer is called the regolith layer, and it contains rocks and not as much organic matter as is found in the B layer. There's a B horizon, sorry. There's a lot of organic matter, we hope anyway, in the B horizon. We're going to talk about organic matter in a little bit. And then we've got R horizon, which is our sedimentary rocks or consolidated rocks. And this usually acts as a physical barrier to the roots. So if your roots have got past the C layer, the C horizon, sorry, they will reach this R horizon. The one thing to note about the C horizon is that you do sometimes get, this can act as a physical barrier, and there is sometimes chemistry that occurs in this C horizon that actually stops roots from growing. The chemistry is toxic, but we'll learn more about that later. So is that simple? Do you understand that the soil profile is separated into horizons, and these horizons are different, and they can vary in depth and thickness depending on your soil type? Because that's the few things I want you to take away from this. Is all of this a bit new terminology to you? Yeah, good. Excellent.
Just I'm thinking, so just excuse me. By knowing this soil profile, so it will help me to pick up the right rock.
If you know your soil profile, you are 50% to managing soils correctly. Yes, it is absolutely essential you understand this, and we will begin to cover this in this subject, but it will take 3 years of this degree and probably 15 years of farming commercially to truly understand how to manage your soils in your way. And because soils are, I hope by the end of this lecture you'll really understand and appreciate soils in a new way, because they are extremely complex. And when you're managing a living organism in a substrate that's extremely complex, then you begin to understand that optimizing that for your economic return or your productivity, depending on what you're aiming to do with your particular block, is the key. But I would start, yes, by getting a spade and digging a hole. And usually you need to go about 1 meter down. So a backhoe is better to dig your hole. Okay, so this diagram doesn't come up as well on the with the light behind it on the overhead projector. I've noticed that a few times. But when you actually open your lecture notes in Moodle, you'll see that there is a massive the color scale. It looks far better. But what I want you to take away from this is clearly, this is a map of Australia, right? We've all got that, and clearly there are lots of different soil types. This is according to the ASC orders, which is a classification of soil. And we've got different examples of soil types here. Now, this data was published by the FAO in 2004 and maps, and a lot of this work was done by CSIRO and universities working together to map the entirety of Australia. Now, if you think how difficult it is to actually dig a hole every 1 meter in Australia, that would be, I mean, like, Australia's massive, okay? It's huge. And so that would be a lot of resources and a lot of time. So one of the things that you have to note is that some of this is a bit of a best guess, because we haven't taken a hole and dug and analysed every metre squared. But we have, in regions where there's a lot of farming done, so if I can find my mouse, where have you gone, mouse? So, oh, there we go. Down the south here are how much sampling we've done is better than in the middle or up here where there's not so much commercial farming. So just note here. But I think you can see that there's lots of different colours across Australia, isn't it? I think we can safely say that there's nothing uniform. And even if you come down to Victoria, is it uniform across Victoria? No, no. So this map, if you take nothing away from it, please note there's a huge amount of variability in our soils in Australia. In fact, we have one of the most varied developed countries where farming takes place. Then, you know, it really is, and it makes it a challenge, because each one of these soil types means that you may have to manage your soils slightly differently depending on what they're constructed of. So what we've got here is a lot of what's called sorber soil around Victoria and around Melbourne. We do also have other soil types, but this is what sort of predominates our sort of area around Yang Ying. On the property at the farm, we have 7 different soil types, and it's so varied that the Soil Society did their conference there a few years ago, and we dug 7 pits for the Soil Society of Australia, and they came in, and they're a whole load of soil science nerds basically, and they got hugely excited by the fact that we had so many different across what's only a 200, well, it's a 250 hectare area is where the soil is different. So, you know, that's just one property, 7 different soil types. So it just goes to show. And even across a paddock, even when you've defined you've got X soil type, you probably have variations across that, because soil is not uniform. And it's not uniform because it has complexities in what? Texture? What else? Organic matter, yes. What else? We've covered it. Tick-tock, tick-tock, tick-tock. Time, yes, and chemistry. So all of that comes together and can change. Rain doesn't fall uniformly, does it? So you can get some areas of a property that are subjected to a lot of rainfall and other areas that aren't. We get that at Yang Ying. We have what we call rain shadows, and that's because of the mountains at the back, and they stop the rain falling uniformly across the property. So we have paddocks where we know we know the soil type, and yet part of the paddock has been exposed to a lot of rain and part is in this rain shadow, which means we get different texture, different changes, because there's more, the more rain we get, the more rain and drying, the more physical movement in the earth, and the more breakdown we get. So you can actually see that on our property. So organic matter. This is a source of a lot of nutrients and a lot of nutrient cycling for the plants, and it is extremely important. As a rule of thumb, do you think Australia's organic matter is high or low? No, it's pretty pathetic actually. It's very low. And it is causing us, we believe, some problems in certain areas in Australia, particularly if you've done a high intensity cropping type situation and you haven't encompassed pastures. You're just taking and taking and taking, and you're not replacing. So minimum till has helped with that. We'll talk about that in a few weeks, but yeah, it is a problem. So what is organic matter? Well, it's just living components. So it might be bits of the plant that have broken down. It might be manure, that sort of thing. That all makes up the organic matter. It might be branches, bits of stick, all sorts of things. It's an extremely diverse component of the soil. It aids soil aggregation. It also aids to soil structure. And it also provides great properties for water use and holding in the soil. It tends to be hydrophilic, water-loving organic matter, and it also helps with creating aeration or air spaces. And organic matter tends to, as a rule, land on the surface of soil, so that might be with you slashing back your crop, or it might be with a cow pooing, that sort of thing. And then that slowly breaks down and goes through the soil surface. And as it goes through the soil surface, different things happen to it. Well, it clearly breaks down the organic matter, but it changes things as it's moving down. One of the most important and highly complex roles that organic matter has is definitely in nutrient cycling in plants, which you will learn a little bit here today, but most of it you'll learn in ecological systems. So Why is soil important for crop growth? Well, it has many functions. It's actually, if this is your soil, it's actually a medium for the plant to sit in. So, you know, this is my plant, this is my soil, and it actually holds the plant down. It enables the roots to act as an anchor. It enables the roots to take up water. It enables the roots to take up oxygen. Very, very important. It enables the roots to take up essential nutrients. It's definitely required for plant growth and development. And you can see lots of data on the literature. There's hundreds and thousands of papers describing how different soils impact on different plant growth rates and returns. So you could have a growth cabinet with everything in that cabinet being set, and you can have some plants in one type of soil, let's say a calcitrate type soil, and another set of plants in a sandy loam, and you will see that those plants will grow differently because those two soils absorb water and they absorb nutrients differently. Everything else about that environment would be identical. They'd get the same amount of nutrients, they'd get the same temperature, humidity, wind, everything else. Just changing the soil can change things dramatically. There are also symbiotic relationships with nitrogen-fixing bacteria and other bacteria that fix other components as well. And of course, it's a storage of water, which is very important for us. Mustafa, answering your question, if you understand the soil profile and you understand that most of your water is stored in B1, B2, and some in C, then if you're irrigating, for example, some of your crops, which you may be doing with some of your trees, I don't know, then you can sometimes, a farm manager will irrigate to keep soil moisture below and build it up for the drier summers. You might do that in the winter, for example. The bigger the depth of your B and your C horizon, assuming that it's hydrophilic, the more water storage you can get. So if you're working in a soil structure that only gives you your B horizon down to 20 centimeters and your C horizon maybe down to 45, which does occur in some instances, then your anchorage point for your roots is very shallow. So you wouldn't want to plant big almond trees in there, for example, because there isn't enough anchorage. You wouldn't want to put citrus or grapevines in there because you really do need anchorage. But if you were growing pastures, that would probably be okay. You would just need to note the amount of water that you could store in that area is not great. So this is something called the soil food web, and it's really quite a basic concept in that you get lots of organisms in your soil, and these organisms will move components of nutrients and cycling in the soil. So this is the soil web. So we've got plants as part of this, obviously. We've got organic matter, and then we've got living things in the soil. I always say, if you're ever going to buy a property or you're looking to manage a property and you want to have an idea of the soil health, a really simple test is to get a spade and dig a couple of spade depths down and then look at the soil. If it moves, if it's full of a whole diversity of stuff, right? If you can see different bugs, different insects, different fungi growing in by the color, you've got a healthy soil. If you dig up your soil and you see nothing move, you see no fungus, that's not good usually. Or if you dig up your soil and you only see one kind of bug, so let's say you only see one kind of worm and nothing else, again, that probably isn't a very healthy soil, because even a beneficial, if it becomes too great in its population number, can then become a pest. So the balance of this food web is really important in soil health. It can also help fight off diseases and keep nutrient cycling going. There's a video here you can watch in your own time. This will show you soils and examples of soil ecosystems. So it's a very pretty web-based video, which you'll skip here. So when we're talking about soils, we said one of the most important components of soils was that it was carrying of nutrients. We're going to learn in the next lecture about some of those nutrients that are important. But soil predominantly carries most of the essential elements that you need for life. So what we're looking at here is CO2 and oxygen, CO2 out from the plant, oxygen into the plant. We've got water, but we've also got these nutrients. We've got micronutrients and we've got macronutrients. So all of this makes up a good, what we call essential elements that are found in the soil substrate. Typically, there are about 17 of these elements that are essential. There is some discussion about some other micronutrients. There's a fair bit of debate about some of them, things like silicon, for example. So when we're looking at soils and we want to understand how good some of our essential elements are, one thing that we can look at is our carbon to nitrogen ratio. So we calculate or measure the amount of carbon in the soil, we calculate the amount of nitrogen, and then we put one figure over the other, and that will give us what we call a ratio. So hopefully you're all akin with what ratios are. Now, the amount or how that ratio differs will alter how quickly or slowly a plant matter decomposes. And so the CN ratio among plant ecosystems can vary. So we have a CN ratio in soil humus of 10:1, which is quite ideal. In garden soil, depending on how much manure and compost you dig in, that can change from 12:1 to 15:1 range. Here is an example of a young alfalfa soil. That's a soil grown with alfalfa. We have a compost here, and you can see again the C to N ratio, and this gives you examples of how this may vary. So we've got clover residue where it's 23:1, and then straw, for example, is 60:1. So the higher this number, the higher the amount of carbon, the more organic matter in the soil. So we have something called organic matter fractions, which is basically, as the term describes, it's the fraction of organic matter. And we have a suite of organisms that play a role in that organic matter. Now, do we all know the role of earthworms in soil? Are earthworms good? Most of them, not all of them, but most of them are good. And a mix of species of earthworms. There's quite a lot of earthworm species. An earthworm isn't an earthworm. There's lots of different ones. And you see ones that are very skinny and move very quickly, and there are ones that are bigger and move slower, and they're different species. We have things called potworms, arthropods, nematodes, mites, etc., and then we go all the way down to fungi and bacteria. And all of these constitute and move around the organic matter fraction. So here we've got their approximate length. So earthworms are quite big in the soil community compared to our fungi and bacteria, which are very, very small. Our populations tend to change inversely from our population size. So in other words, we have a handful of worms in a meter squared of soil. We have millions of microbes. Okay? We have approximate biomass, and that ranges depending on what the organism is. So earthworms tend to have a biomass of 25 to 50 kilograms per hectare on a dry weight basis, whereas microbes are 500 to 750, and this is just because there's millions of them. And this gives you an example of how the scale or number changes per meter squared. So sequestration of nutrients and carbon, that is the movement of or changing of the form of the nutrients. That role is very important for organic matter, play an important role in the sequestration of nutrients. We also know now that the organic matter produce, they're a source of nutrients. So you can add X kilograms of NPK, and then the next day you can go and measure it, and it will be different to what you've added, because there is already some of that NPK in the soil, you hope anyway, and it's continuously being cycled. There is a component of soil aggregation and structure where organic matter play a role in, water storage and chemical sequestration, which we talked about. So this is a little bit on earthworms. I like earthworms, and you as agronomists should really like earthworms too, because they play a really important role in soil structure and recycling of nutrients. I have pot plants as well as a garden, and I will often take a couple of my earthworms periodically from my garden and put them in my pot plants, because they play such an important and good role, and they move, and they as they're wiggling around in the earth, they're causing hole pockets which can either be filled up with water and or air. So that physical movement is important, but they also play a breakdown because they absorb organic matter, and then they have waste, and all of that plays a role in the cycling. It's a very complex role. Trials have shown that up to 40% increase in pasture production can be found by increasing the number of worms in your community. So what other soil properties play an impact on your plants? Well, we've got texture, we've got structure, we've got chemistry, pH, and cation exchange. So let's learn a little bit about this. Let's start with the soil texture. So when you took your soil, you took a little bit in your fingers, hopefully, and you felt, you just rub that together and you feel how that texture, you can actually feel differences in soil texture. So if I had 6 or 7 different soil types and you put all of them in your finger, they would all feel slightly different. Some are very grainy, some are very smooth, just to give you an example. I would encourage you, now that you're being introduced to soils, is to go home, either in your own property or your own back garden, even your pot plants, and just put your fingers in and feel the soil texture, and get familiar with feeling different soil textures, because building up that knowledge is really important. So the texture describes the soil fineness or coarseness of, and you'll be able to detect that with just your fingers. There are tests which can define soil particle size, which gives you a more quantitative measure as well. So we have sand and silt, which are made from silica. We have clay. We have aluminium, oxygen, hydrogen, potassium, magnesium and phosphorus, all chemically reactive and all provide components for plant growth, which are very important, but can all determine and influence your soil texture. I think sand plays the biggest role for you as agronomists. You can really tell high sandy soils compared to low sandy soils. It's a very, very easy test. So even if you can just start with determining, looking at it and feeling it and seeing, is this a soil with a lot of sand or not? The other thing that's very easy to differentiate is clay. Different types of clay are quite a lot more complex to differentiate, but clay tends to be, like very soft and malleable. You can move it easy, whereas sand isn't soft. It's hard and it breaks and it crumbles. So this is what we call the soil triangle, and this is something that you'll see a lot when referring to different soil types. And it really is quite useful for you to get familiar and learn this. So we've explained that different soil types are composed of, are made up of different things and different proportions. And there are 3 main constitutes of soil. We have sand, we have silt, and we have clay. So depending on how much sand or how much clay or how much silt is in any one given soil can tell us the different types of soil composition. So if you have a lot of clay and no sand and a little bit of silt, you'll be here on the triangle. Whereas if you have a lot of sand, very little clay and no silt, you'll be here. So this is a very sandy soil. What we've discovered is that we can characterize these by the proportion of sand, silt and clay. So if you have a medium loam, for example, you'll have some clay present, some silt present and a fair bit of sand. So does that make sense that you have different types of soil composition and that they vary depending on your relative proportions of clay, sand and silt, and that triangle is showing you those relationships. Any questions on that? Yeah?
In terms of profile, what would you press silt, sand and clay?
So I think what you're asking me is, does the soil composition change between, say, A horizon, B horizon and C? Yes, it does greatly. Excellent question. And there is no linked relationship. It all depends on how the soil has evolved and what its base minerals and rocks it's come from are.
So you would have a layer just silt.
You can have a silt layer followed by a clay layer, for example. Yes, that can occur. Different countries and different soils around Australia have different compositions of clay, silt and sand, and we can actually see a lot of different examples. And when you go out with Doug and he goes and digs holes for you in the ground, I'm gonna hopefully dig out a hole as well for you guys later on in the subject when we go out to Yangying, and you'll get into you'll actually see and get in to see an example of some of the soils that we have. But yes, they can change. Is there a direct correlation? Do you always get a silt followed by a sandy loam followed by a clay? No. It really depends on how that soil has come about, which depends on where it is on the earth and what it's formed from. Did it form from sea sediments, or did it form from rock? Or what mixture of rock and sea sediments, as in Australia, did it form from? So understanding the geology really helps you understand the soils. Okay, the next thing we're going to touch on is structure. So these are some examples of soil structure. We have a granular structure. We have a what's called a massive structure, a single grain, a blocky, and a platy. Now, these are, if you were to have a microscope and look at this soil or any soil, the soil structure definitions and descriptions would become a lot more obvious to you, because that's what they're based on, what they look like when you blow it up as a microscope. But it's like a shape of the soil, and different types of soil will have different structures. So why is soil structure important? Well, it adds volume and the arrangement of the pores in the soil. So if you have a structure of soil that's quite large, you're not going to have as many pores as in the same area than if you have a structure that's very small. All right. So what does pore size change? Can you remember? We touched on that at the beginning, or earlier on in the lecture. Excellent. Water storage, and what else does it change? Two things. What's the second thing? Yes, great, excellent. The amount of oxygen. This determines soil moisture movement and airflow in the profile. This affects soil, what's called friability, which is basically the word as it describes, that you say the soil's fried, which you're basically meaning it's damaged, it's no good. So the ease of rain infiltration and runoff, cultivation and growing plants are all influenced by your soil structure. So Mustafa, so not only do you have to know what each of your horizons are, you need to also know what their composition is and texture, and you need to know what the soil structure is. The soil structure will be influenced by the texture as well, which is influenced by how it's made up. So damaging soil structure can have big influences on either your livestock or your plant growth. And you can see changes in channels if you get compaction. So what's compaction? Do we know what compaction is? Yeah, that's right. It's very simple. So if you have a tractor and you're spraying every couple of weeks and you're using the same lines, directly under that wheel you are compacting. And if you go once or twice up and down the paddock, you probably won't see a big problem. But if you go up every fortnight, as sometimes you have to, and you get rain and dry, up and down the paddock, more rain, more dry, more rain, more dry, you will see big problems with compaction. What does compaction do? What does it change? That's right, yeah, it squashes the air out, it squashes the water out, literally is, and it makes the soil more hydrophobic than it would have been previously. So that's all problems. We also have problems with erosion, and erosion is loss of viable soil, and that can be that used to be a massive problem in Australia before minimal tillage was brought in. There used to be these massive dust storms. Have you heard about these? You must have, you know, and suddenly whole cities were covered in dust and whole towns because the wind would, you know, they would grow the crop, they would harvest it, they might turn it over, and then suddenly all this topsoil was just blown away across Australia. And if your structure was light and small, you'd get more of your soil lifting off. Why is that not good? Why is it not good to lose a bit of your soil? Yeah, that's right. You're losing money. Every time that wind blows and you let that paddock stay bare, you're losing money there. So if you are going to keep it bare, try not to keep it bare when it's extremely windy. So you want to stay away from periods like September. So if you have poor structure, that will cause more erosion, and you can see that you're 5 to 10 more likely to get erosion with some soil structures. So again, understanding your soil structure will then help you manage your property and what you might do to avoid the loss. Identification of poor soil structure, well, you'll have what's called rill or sheet erosion. You can get surface crusts as well. I don't know if you've seen this on your own garden or on paddocks, but the soil actually looks different when it's starting to erode. You sort of can sometimes get a glistening on the top of it, and you can see that changing as erosion occurs. You can get what's called cloddiness, and also there can be plant indicators. So if you've got your paddock there and you get more of these toad rushes infiltrate, for example, that can indicate a poor structure.
What's the problem?
It's a type of plant. I can show you some pictures later on when I'm on the internet if you want. You get ponding, you get hard surface and poor infiltration, i.e. we talked about that earlier, so when the rain falls, the water isn't going into the soil profile, it's washing off, and that's no good. And it can also change the presence of organic matter. So a bad soil structure can reduce the effectiveness of your organic matter. So soil structure action, this enables permanent pasture establishment, can really help with your soil structure. So if you've got bad soil structure, stop cropping, put a pasture on it, put some animals on it. That's usually one of the best recommendations. Manage the pasture well with respect to your water, your nutrients, and your light grazing. So you don't want to encourage a lot of grazing, because what will happen with grazing? What do animals do? They compact, yeah. Particularly horses. We haven't got a horse person here today, but if you're online, horses, yeah, big problem with compaction on some soil types. You can add a chemical called gypsum, and that can help with building up your soil structure and amending it. And there's a test that you can do to determine what your soil structure is and whether you should add gypsum, and you can go to an independent company for that advice. We have rates of gypsum, usually about 2.1 tons per hectare is the standard, but you really need to have the soil measured and then determine what and how often you should add your gypsum. Usually it's a long-term strategy. This isn't a one-off application of gypsum. Normally you're looking at quite lots of hundreds of dollars, and you know, several applications over a year for several years to build up bad structure. It's a lot harder to repair bad structure than it is to manage good soil and keep it healthy. That's usually the avoidance is the best tactic you can. There's an exchangeable cation level test which can indicate your soil structure, and that can also help with understanding your gypsum application rates as well. So we've talked about texture, we've talked about structure. Now we're going to talk a little bit about chemistry. So do we think chemistry is important in soils? Yeah. Do you think it's complex? That's a bit of a loaded question there. Yeah, it is. Everybody's nodding for those online. So soils have many chemical properties and they impact on the plant growth. If you saw a couple of slides ago, we had a whole list of the bugs, you know, the groups of bugs, not just the, not the species. You can see that's really diverse. We've now discovered that structure can be really diverse, as can texture, and all of those can interact with your soil chemistry. One of the most important measures of soil chemistry is what we call the cation exchange capacity. So you get ions in soils, and some of these you get particles, with positive charges and particles with negative charges on them. And whether your particle is positive or whether your particle is negative will impact on the chemistry of that soil. That also impacts on your soil pH and your salinity. It also impacts on your nutrients as well. Do we understand what soil pH is? Do you understand what pH is? Yep, because you've all done that in living systems. You all understand the hydrogen ions. It's a quantitative measure. Yeah? Good. And salinity, what is salinity? Excellent, yes. And do you know what the chemical formula for salt is? Sodium? Yeah. Sodium chloride is one salt. There are many salts. Sodium chloride is the predominant salt. Is salinity a problem in Australia? Yes, in some areas. Not ubiquitously. It's not so much of a problem in Tasmania, not south of Victoria, but yeah, certainly when you go up to places like the Murray-Darling or where you've had extensive irrigation systems in place, it can be a problem. Salinity is extremely difficult to fix, but can be controlled with good sensing and good understanding. Okay, so let's talk about the cation exchange capacity. Here we have a figure which hopefully helps you understand this a little bit. So we have examples of negative charges in particles. So a little bit of a rock or a clay molecule or a sand can all have a charge, and that charge can be positive or negative. Not only can it be positive or negative, but it can be strongly negative or strongly positive. So there's a whole scale of differences. And the charges will either repel each other or they'll attract each other, depending on whether they're opposites or not. And so when you look at this, this is a sort of a theoretical mix of, we've got magnesium in here, we've got calcium, we've got potassium. So we have, some of these molecules have a 2+ and some of these have a 1+, and that indicates the charge. So there's 2+ ions or 1+ charge of an ion. We have what's called cations and we have anions. And in our soil matrix at any one time, that is changing, that is diverse, and it changes all the time. If you add water to that, that'll change again. So I wanted to show you this because I want you to understand that a soil particle might not be uniform in its charge. It might have slightly different areas of being positively and negatively charged, and then you have different compounds attracted to that through the charges. So if you were to get a piece of this soil here, a tiny, tiny piece, and we were to put it under a special type of microscope, we might see that this humus particle had a sodium, a magnesium, a hydrogen, several hydrogens, and a calcium attracted to it. So if you were a plant root and you were growing along here and suddenly you came across this humus particle, this would be like hitting gold because suddenly you have all of these compounds that you can take up with, you know, that are attracted to that particle. However, they can only be taken up by the root if the humus particle and the compound can be separated. So depending on how strong that affiliation is will depend on how much your root can take up. And this is where soil composition plays a big role, because sand, for example, it only tends to weakly attract, whereas clay can have particularly some kinds of clays can have really, really strong attractions. So you might have a lot of calcium, potassium, magnesium in your soil, but if your clay particle is such a chemical composition that it's really holding on, then you'll have some problems. And this is what we mean by available nutrients. So we're not just interested in how many nutrients or the concentration of nutrients in the soil. What we're most interested in as agronomists is how much of that is available to the plant at any one time. And that's called the availability. And that is really determined by the chemistry, the structure, and the texture and composition of the soil. All of those things play a role in the chemistry, which then plays a role in how accessible nutrients are. So we can understand that relationship. And that's is not uniform for all compounds. It changes, and it gives you a bit of a scale. So aluminium has a very, what we call, strong cation exchange capacity, whereas sodium, for example, is very weak. And this scale here ranks them relatively. So aluminium is stronger than hydrogen, which is stronger than calcium. You see that it ranks down. So cation exchange capacity plays a role in supplements and nutrients, and how you add them and what you add is important in that in understanding that. Another component of soil chemistry is acidity, or pH, or the amount of available hydrogen ions. When pH is 1 or 2, it's very acidic. When pH is 11 or 12, it's very alkaline. What do we ideally aim for in soils? Acidic or alkaline? Sorry? No, we aim for neutral. We're going for the middle. Now, one thing you'll learn about soil chemistry and about nutrients is that everything in growing plants is a compromise. If your pH is about 7, you're neutral. Now, most soils in Australia that are farmed commercially usually are somewhere between just north of 5.5 up to about 7.8. 8 is pushing it a bit, to be honest. And if your soil is more alkaline, you'll get different nutrients available to the plant. And if your soil is slightly acidic, you get a different set of nutrients that are more available to the plant. And that's because charges and availability of ions are ranked depending on what the compound is. So if you couldn't have a soil that was completely neutral, somebody joining us on Zoom, welcome. Can't see. Hello, who's joining us? Okay, well, hi, whoever's joining us. For those of you who've forgotten, we do have students coming online and joining us in the classroom today, so just to make that clear. So what we have here is we have acidity, and we have that can affect the how many nutrients are taken up. And if you didn't have a soil that was neutral, would you prefer it to be slightly acidic or slightly alkaline? No, actually acidic is slightly better because there are a few more nutrients available in slightly acidic than there are in slightly alkaline. But you're not to know that at this stage. That was just a good guess. But you could have gone either way, right? So yes, so you tend to be able to farm in more acidic soils than you can in more alkaline soils as a rule. So consequences of low pH means acidity, is that it prevents legumes forming nodulations, which impacts the nitrogen cycling. The recycling of nutrients is another component, and pH in itself can cause toxicity to plants. So all of that's pretty important. We have a release of aluminium when your soil is very high, low in pH, and also manganese levels, particularly in hot, dry, and poorly drained soils. And that can become, you can get aluminium toxicity and then manganese toxicity, both of which are not good for your plants. You have a decline in nutrient cycling, and therefore you have a decline in nutrient availability. When we say aluminium and iron, we sometimes refer to it as tied up. And it's there in the soil, but because the pH is so low, it's not available to the plant. And if you ever hear people talking about tied up, the nutrients tied up, that's what they're referring to. It can cause molybdenum. Can you all say molybdenum? It's the hardest nutrient to say. Practice it, molybdenum. But low pHs can cause molybdenum deficiency. So there are a range of effects of low pH soils on plants. Most of them seem to be, from a growth and development perspective, and they will reduce yield as well. This is a very useful figure, which you'll see in and around the literature, and you also find on the internet. And it's a summary of how pH can affect soil fertilities and the associated nutrient availability. Just trying to find my mouse. Where have you gone? Right, so this is neutral. This is what we call alkaline soils, so pH greater than 10. And this is what we call acidic soils. So this is extremely toxic to plants if you're at pH 3. 4, it's still toxic. 5, it's moderately toxic. So we have some soils at Yanying which are about 5.5, 5.4, and we are liming them. We are trying to address that to bring them, better towards 0.6. But you can usually only move it 0.1 of a pH per 2 applications. So it takes a long time. It takes a couple of years. Our optimal pH is neutral, but anything, about 6.8 is great. If your soil 6.8, 6.9, 7, 7.1, 7.2, you are going to absorb most of the nutrients that you need in an effective way. Then as we get higher in that pH scale, so we go to 8, it's slightly alkaline and you're slightly impacted. Up to 9, you're moderately impacted and you're really beginning to see impacts. And up to 10, it's all game over for you. You've got a real problem to manage there. Now, we use grade B water at Yanying when we're irrigating, and the council provide that to us, the water authority, provide that to us. And when the water hits at 9, they stop the release of water because they recognize that it's a problem for us, and you don't want to have that problem on your soils. So is that graph or figure quite understandable to you? And it's certainly one to learn because it really does sum up nicely and gives you that scale and understanding. Okay, so uneven pasture growth can result when you've got acidity symptoms. So you can see that, sometimes you can, if you're looking at the paddock and you see patches where it grows well followed by patches where it doesn't, and that can just be a change in acidity in the soil. And again, you can manage that by adding conditioners to just that area. If you determine, you take a soil test, simple soil test to do pH, we can all do. And and we'll talk about that later. But yeah, that's something that's quite easy to manage, and you can certainly add spots of managing it.
And you take a sample from the top of soil, or
Good question. We will cover soil sampling, but really you need to understand your A, your B, and sometimes your C. So you need to go down. Usually most soil samples would ideally go down to, well, it depends on what you're managing as well. So for example, in a grass or pasture situation, you'd want to do a soil sample of 15 to 20 centimeters. In an orchard, you'd want to go down at least 80, if not a meter, because that's where your root zone will be. So where your root zone will be is where you sample from. However, sometimes you want to understand what's going on below your root zone. So you may. Yeah, look, it depends the question. Soil sampling is all about the question you're trying to answer at the time of sampling. So if you're trying to answer how much nutrients are available to my plants, you would take the depth where your roots grow, and you would homogenize it, mix it, and because that's what would be available to your plants. So you take your A horizon, you take your B horizon, you'd scoop it out, you put it in a bag. You could either take it with an ergo or you put it in a bag, you mix it up like this, shake it. It's all very technical, this is how it's called. Then you put it in your beaker and you'd add either a substrate or water. So water tells you something about pH. Some of the substrates that you do tell you something more, but we're not going to cover that depth in this lecture today. But yes, do understand there are different types of pH tests. We're going to do the water one, which is very simple, but sometimes you need to do other ones because you need to understand more of the chemistry. So it causes bad nodulation, stunting of root growth as well. Okay, action. What can you do? Well, you can add soil conditioners, and that can change your pH issues over time. It can be corrected in some instances. If the pH is too extreme, then sometimes it can't be corrected, as they found in the Murray-Darling. There are areas there where it's just so alkaline that anything they do at the moment. There is some research using things like algae to correct for soil pH when it's extremely acidic, and that's looking quite promising, but it's still a long way to going from commercialization. When you look at your pH issues, you want to understand them quantitatively first. So you take a number of soil samples, and depending on where the pH problem is will depend on where you take the soil sample. So if you've just got a pH problem in your horizon B, you would dig down to then take your sample. If you've got a pH problem with horizons A and B, and that will depend on your soil structure and your soil, what your soil's made of, basically, where your problems will be. Lime is a common, what we call conditioner for soil. So that's just, like your hair conditioner. You put it on the soil and it makes it better. And you will you spread it on. Usually we get contractors to do it now, and they've got all the equipment, and you can spread it on. You add a number of applications. It's normally several $100s per ton, and you normally have to put several tons on your paddock, but that will depend on the size of your paddock. There is a mode of action, so it changes by neutralizing the pH. And here we've got a guide, 2 tons per hectare gives you a 1 pH change. So if you've got a paddock of 5.5 and you want to bring it up to 7, that's a lot of applications of lime over a lot of time before it will change. Years, normally to change something from 5.5 to get it up towards 7 is usually a 4-year plan of at least 2 to 3 applications per year. And not only do you have to think about that, but you have to think about when you're applying it. So if you apply it in the middle of the summer and it's quite lightweight and you get winds through, what's going to happen? Yeah, dust. It's going to be dust, right? Not going to be very helpful. But if you apply it a few days before a heavy rainfall, it's more likely to be infiltrated into your soil and therefore useful. So you have to think about application rates and timing. So if you do nothing, then your plant yields, your pasture will get worse. If you do something though, you can stop the problem getting worse initially, and then over time you can build it back up as your conditioner works. You will also see, if you have a pasture, you'll see your annual weed seeds in your pasture will change as your pH changes as well. So sometimes you can indicate how bad your pH is problem just by looking at what plants are growing there from a weed perspective. So one of the things we talk about when addressing pH is to change your farming systems. So if you're cropping to go to pastures, for example, that can be a way of addressing it long term. Change your grazing management if you have a pasture as well. If you have an intensive production systems, you might want to look at that and review that and change it. So better nitrogen management will help with pH, as long as soil management. Yeah?
Would gypsum and lime go hand in hand with each other? Or is it two totally different?
They have a different mode of action, and so they you either tend to select one or the other, to be honest. So, okay, so increasing problems of soil salinity, as we've discussed in Australia. There's dry land salinity, and then there's which occurs naturally because of the formation of what's in the soil, how the soil formed. Or there's the most common, which is formed by salinity coming through irrigation water. And the other thing to understand about salinity is it moves as the water profile moves. So if it's rained a lot, it will, if it's down on your C horizon, it will move up through your B and to your A sometimes, depending on how much water you've got. As the summer goes on and your soil profile dries, so does your salinity problem. It moves down. So if you put soil sensors in, and if you measure salinity in your soil sensors as well as your soil moisture, you can watch your salinity change, and then you can manage your soils accordingly. Causes of salinity are land clearing. Traditional practices using clover and pasture have resulted in high levels of water in the subsoil, and this has caused problems. The effects of salinity, well, I think we've all seen it really, but there's an image of pretty, that's quite extreme saline areas, and this was taken off the Department of Primary Industry's website as an example. So when water is in the soil, when you've got salinity and problems in the soil and there's water, it's not used for deep drainage of the water table because when you put too much water on your soils, you can move your water table, so that's how much where your water is, and then that can move your salinity problem up or moving down. So a lot of salinity management is looking at how you manage the soil table. Also, if you have a lot of salt in, say, your B2 horizon, and you irrigate a lot, you can wash some of that out into the water table and then pollute your neighbour, which is not so cool if your neighbour finds out, and you will be liable. So you need to watch that. Other problems with salinity is overgrazing. By reducing leaf area, this lowers plant water use, and that then changes how much water and salinity moves, because if you have less plants, you've got less evaporation, so the water profile will move by how much green matter you have, so that's important. Annual crops and pastures, they have different impacts, so you have to look at the rooting impact. So shallow rooted vegetation systems will be different to deep rooted vegetation systems, for example. You can also control salinity by your sowing rate, and you can change your sowing rate depending on what you're trying to do. So just look at sowing rates. When to sow is a good management technique that can change a lot of things actually. So salinity results in poor pasture and crop, and this can lead to increased disease susceptibility of plants, which makes a lot of sense. Both directly and indirectly it can impact. Long fallows. Fallow aims to store water, and often the soil is full before the crop is sown. So additional rain recharges the groundwater. So that's something to bear in mind. A big problem in recent years has been leaky and damaged degradation of dam walls. So I know a company now that is doing aerial monitoring of the texture of dam walls to predict if they're eroding, and then predict if there's salinity problems because of that. So that's on the increase. There's a lot of farmers after that surface. I was just speaking to a person who does it the other day. We have poor surface damage, where water lying on the land powers plant growth and water use. This then leaks into the water table, so that's another way that can cause you problems. We often advise farmers that salinity isn't really a farm problem, it's actually a catchment or a large area problem. If you've got a salinity problem, your chances are your neighbour's got it as well because of the nature of it. So knowing that means that you have to think effectively about a plan and understand that there's a large impact. So what your neighbour's doing, if they're a few metres away and up the hill, can very much impact what you do and how you manage things, because you have to manage their impacts as what they do as well. So more water efficiency helps you manage it. Native trees are a good way of helping manage it as well. Perennial pastures tend to be the go-to advice, put a pasture in for a while. And usually you take about 10 years of your pasture, 8 to 10 years of your pasture being in there before you start to see changes. High water use cropping, early sowing varieties, and avoid disease with crop rotations, which also helps as well. Organic matter as well, introducing organic matter, and surface draining to repair any leaky dams. Or if you've got, like in Yanging, in our paddock 5, which is the first paddock you come to, we have a lot of wash off that comes down from all 360 basically, because it's sort of a bit of a basin there. And so we're going to put in channels to move that water off that paddock because it suffers so much from all the water coming in. And we see problems there. And use groundwater irrigation and for stock as well. Erosion. This is a problem as it accelerates the obvious loss of water. And things like introducing tillage can reduce erosion. How you manage your soils and your vegetation and minimize your exposure of your soils is basically how you manage erosion. There is something called estimating ground cover, which is exactly what it says. If you've got a lot of ground exposed, you're going to have a lot of what? Erosion, right? And you can quantify that by measuring where it's green and where it's not. And so I want a lot of exposed ground. This is some examples. This one on the left is about 10% coverage, and this one's about 80% coverage. And I think it says it all, really, just looking at the images. There's lots of ground grass plant cover here, not so much here. You're going to get a lot of erosion here, not so much here, are you? You're not being exposed to the wind. And the impacts of rain physically on the soil can change as well. So having the plant, that can break up the physical impacts of that rain falling. And then that causes better infiltration of that water, so you get less runoff. You get a lot of runoff on here. The soil, that infiltration layer will become hydrophobic very quickly on this soil, in this pasture, but not so quickly on this pasture. So in summary, we've understood and defined soils now in a new way. We've understood their texture, their structure, their chemistry, and their biology all play a really important foundation role. We've looked at ecosystems, we looked at plant growth and development and soil fertility, and we've looked a little bit at pH and also a background cover. I think this is an excellent time for a break, and we'll come back in 15 minutes. Okay. Any questions quickly before we go? No? Cool. Probably all tired.